In this video, we're going to look at calculus with parametric curves. So here you see we've got a curve, x is given and y is given as as a function of a common parameter t. And assuming these derivatives exist, then we can use the chain rule. So if we look at dy dt, then by the chain rule, that's the same as dy dx times dx dt. And then in order to be able to work problems where we compute the equation of a tangent line, then we'll need to be able to solve for dy dx. So doing that leads us to the formula that we see in the box down here. So assuming that all of these derivatives exist, and also that dx dt is not zero, then we can get dy dx using this formula. All right, so let's consider the curve given parametrically by what we see here. So x equals 5 cosine t and y equals 4 sine t. And I find it helpful to compare this curve to, or to think about, well, first you could think about the unit circle, which the unit circle parametrically is x equals cosine t and y equals sine t. Over the same limits there, 0 goes from, or as t is an element of 0 to 2 pi. And so just to kind of understand what this curve gives us, well, just look at these numbers here. And so what it does in the x direction, it sort of stretches, in a sense, the unit circle out by 5 in both directions away from the y-axis, and similarly for y with that multiplier of 4 there. So what we get here is an ellipse, and it is traced out completely as t goes from 0 to 2 pi, and it starts over here at the point 5 comma 0, and of course you see the direction from the arrows there. And as you can see, there's a particular point that we're going to investigate with that red line there. So we'll look at that in just a second. But so here we have the ellipse, and again, like I said, you can think about what happened in a sense to the unit circle to get these this x and y. So in my opinion, this looking at ellipses this way and comparing it to, if you started with a parameterization of the unit circle and thinking about what happened to the unit circle, which way was it stretched and so forth to get this, is, in my opinion, I think it's easier to broach the subject like that instead of using purely Cartesian coordinates with no parameter there. Okay, so when t is equal to pi over 6, then, well, what point are we at? Well, if we plug in, just plug in pi over 6 for t and use basic trig, then you'll see that the x value is about 4.3 and the y value is 2. And so that's that point that we see here. And what we're going to do, as you can tell from the pictures, we're going to compute the equation of that tangent line. But of course, in order to do that, we need not only the point, which we have the point now, but we also, of course, need the slope of the line, and the derivative dy dx will help us to do that. So let's look at dy dx, the calculation for that at this point. So first of all, dx dt, let's see, we'll need to compute that. And remember, we're using this new formula, dy dt divided by dx dt. So let's go ahead and calculate each derivative with respect to t. And so dx dt, let's see, dx dt would be negative 5 sine t, I believe, and then dy dt would be 4 cosine t. And so I think that's what we should see. Oh yeah, that's what I have here. So dx dt and dy dt, and then use the formula for dy dx and what we just calculated, and we get this. And so once we get dy dx in terms of, in this case, the parameter t, then we can plug in t equals pi over 6, and that'll give us the slope of that tangent line. And so that's what we have now. So again, just plug in t equals pi over 6, and we get the slope of that line is negative 4 root 3 divided by 5, and that is approximately negative 1.4. And so at this point, you should be in the habit by now, I would hope, of, whenever you get an answer like this, ask yourself, is this feasible? Does this make sense? Especially since we have this curve already graphed. So if we go look at that line that we just, drew just by guessing, just by looking at the curve and drawing the tangent line, does that seem like the slope is about negative 1.4? Well, the slope's clearly negative, and yeah, I'd say negative 1.4 is reasonable, especially considering that the way I've graphed this is not probably to scale. It looks like I have the x-axis scaled a little bigger. Okay, so now we have our slope, and then we just need to use the point slope formula, and we'll have the equation of our tangent line, right? Because remember, the point, the x-coordinate was 5 square root of 3 over 2, and the y-coordinate is 2, and then now we've got the slope there. So we're just using the y minus y1 equals m times, open parentheses, x minus x1, which I think we all know that. Okay, so that's our tangent line. So now let's look at something else. Let's look at the concavity. So we're going to calculate now the second derivative, right? We've already got the first derivative, dy dx. But what's the second derivative with respect to x of y at this point, right? What we know about concavity, that's concave down there. And so that second derivative should be negative, and so let's see if that pans out. And of course, if it doesn't, then something somewhere went awry, and we'll need to back up a little bit. So what we do to calculate the second derivative is, first of all, this dy dt, I wrote that incorrectly. That should be dy. Whoops. Dy dx, actually. Dy dx is y prime. And once we start with that, then we'll basically do similar to what we did before to get the first derivative. We'll do the dy prime dt in the numerator, and then dx dt in the denominator. And I didn't put it here, but it's similar to what we saw earlier. That's based on just another application of the chain rule. All right, so this is our formula for the second derivative, where, again, y prime is dy dx. And so we already have dy dx. Recall that was up here, so that's from here. And so, which I have it here. So let's look at what that second derivative is. So from before, this is y prime. And since we're about to take the derivative of this with respect to t, I did a little trig there because, of course, cosine t divided by sine t is cotangent t. So that's that. And then, so dy prime dt would be this negative 4/5 times the derivative of cotangent t is negative cosecant squared t. And then the denominator is the same as we had when we calculated the first derivative with respect to x, because it's, again, dx dt in the denominator. And so we do a little trig there, a little simplification, and you get -4 divided by 25 times sine cubed of t. and then to figure out what is the second derivative of y with respect to x at that point, then we'll just plug in. Again, it was that when t is pi over 6, and we'll plug into this formula, and that turns out to be negative 32 over 25. And again, my question was, is it feasible? And of course it is, because that's a negative number, and looking at the picture, again, it's concave down at that point. So that's all that, of course, should match. All right, so lastly, we'll look at an area problem. So what is the area trapped inside that ellipse? And so what we can do is use symmetry and just calculate the quadrant 1 area, right, the area of the region in quadrant 1, and we can just multiply that by 4. And we have to be careful here. We're going to integrate, so if we take a slice, a vertical slice, then the height of that vertical slice is y, and we're taking y directly from our parametric equations, so y is 4 sine t, and we're going to integrate as x goes from 0 to 5. But now think about what is t for x equals 0? Well, I mean, of course, there's 2 times when that happens, right? T goes from here to here, and at that point x is 0, and then t actually keeps going, because remember, t is between 0 and 2 pi. So there, but remember, we're trying to get the first quadrant area. So we're just going to focus on t equals 0 and t equal pi over 2. And of course, when t is pi over 2, that's when x is 0. And when t is 0, that's going to be corresponding to when x is 5. Okay, so we'll see that in a second. Okay, so the area, let's just put this on the whole screen. So the area is 4 times the quadrant 1 area. And so again, we're integrating as x goes from 0 to 5, and then we're integrating y. And at this point, it's basically like a substitution that we learn in Calculus 1, but we're going to do the substitution using the parametric equations that we already have for this curve, right? So x is 5 cosine t, y is 4 sine t. So you do that particular, in a sense, that particular substitution here. And we talked about how to get these limits. That's why I have a star by that, because you have to be really careful there. And so x is 5 cosine t, dx is negative 5 sine t dt. And then just plug in and realize that this is t starts at pi over 2 and ends at 0. And I know that seems kind of backwards, but this is just going to be one of those cases where we can switch the limits of integration and multiply by a negative. All right, so we get 4 times integral here, and then y again was 4 sine t, and then our dx is this part here, and now we just have an integral that needs to be evaluated. Okay, and so the first thing that I did is switch the limits of integration and multiply by a negative. You'll notice that the integrand up here is negative, but here there's no negative present. And I've reversed or switched the limits of integration. The constant is 80 there, and then we have sine squared t. And remember, probably from Calculus 2, I think, where this is covered, is if you need to integrate an even power of sine, as we have here, or of cosine, either one, then just use the half angle formula, which we have here. And so that gets us here. And then from there, it's just a regular old evaluation of a definite integral, so I'll let y'all do that. So we end up with an area of 20 pi.